In section 4.2, we have a few named theorems here. So I think that these are going to be important theorems. These are theorems that I might ask about, say, on a quiz or an exam. The first one we're going to talk about is Rolle's theorem. It says, let f be continuous on the closed interval a to b and differentiable on the open interval a, b with f of a equals f of b. Then there is at least one point C in that interval a to b in the open interval ab, such that f prime of c is equal to 0. Remember, this really means we have a horizontal tangent line. So there's at least one x value where I have a horizontal tangent line. Now, Rolle's theorem, it guarantees the existence of this point, but it doesn't tell you how to find it. But this one's actually kind of neat. I think it's kind of interesting to look at the proof of this just graphically here. So we're going to break it down into two cases. Case one is that f, so our function, attains its absolute maximum and minimum values at the endpoints, which means that this is my absolute max and min values. And then same thing over here. But if this is my absolute max and min, then the right endpoint has to have the same y value. Actually, let's do right about here. This is also my absolute max and min. Well, if my graph were to go up any higher, then this point, or both of these points, would no longer be the absolute maximum. So it can't go up. If I went down, it's no longer the absolute minimum, so can't go down. It means there's only one way this function can look. It must be a constant function. It's a horizontal line, in which case we can take any point we want and sketch in the tangent line. The tangent line to a horizontal line is just going to be a horizontal line. So you can pick whatever x value you want. You're always going to end up with a horizontal tangent line. So in other words, you can pick any x value and the derivative of your function at that x value will be 0. So that's the first case. The second case is that the absolute extreme values do not occur at the endpoints. And so here we might have at least one of them doesn't occur at the endpoint. So maybe you've got your absolute minimum here. Let's say our absolute minimum still occurs at the endpoint. So this is an absolute min, and the absolute min also occurs over here. So if I think about this, it needs to be continuous, which means I can't all of a sudden jump up like this, because that was part of our condition here, is that we said that f had to be continuous. So we can't have any jumps. We know it can't look like that. It also can't have any sharp points, right? So I might say, okay, something like this. And actually, that's not a function, so let me fix that. Otherwise, it's going to bother me. There we go. You might say, well, this right here has no horizontal tangent lines, but this point right here, there's my absolute maximum. But now it's failing another part. It said it needed to be differentiable on the open interval a to b, which means that the derivative must exist everywhere on the open interval. So right here at this point, the derivative does not exist. The derivative at that point is undefined. So we can't have that. So essentially what this is requiring us to have is to have some sort of smooth curve here. Maybe it looks something like that. And we have at least one point where we have a horizontal tangent line. Now, it is entirely possible that we have more than one. Perhaps in this case we've got up to 3. Right? You could have a whole bunch, but we have at least one. So perhaps my graph looks something like this, and we say, okay, here is our horizontal tangent line right there. So we have to have this at least one place, one x value where we have a horizontal tangent line. So we're going to look at just a couple quick examples of Rolle's theorem here. It says determine whether Rolle's theorem applies to the following functions on the given interval. If so, find the points that are guaranteed to exist by Rolle's theorem. So if we think about what the conditions were, and actually let me go back so that we can talk about the conditions. Our function must be continuous on the closed interval a to b, has to be differentiable on the open interval a to b, and f of a has to equal f of b. There's really three conditions that we have to meet. So first of all, is g of x continuous on -1 to 1? And for this, it might help to sketch the graph of this function. This is actually pretty easy to do using transformations. I'm going to sketch the graph of this function over here. Oops. This is, let's see, this is the absolute value of x, which absolute value has that V shape. Let's see, we've gone up 1 unit, and then we have a reflection across the x-axis. So our function should look something like this. So if we say -1 to +1, if we're looking at just this little section right here, just this piece, yeah, that looks continuous to me. There's no jumps or holes or anything like that. So yeah, that's continuous. 2, is it differentiable on the open interval a to b, or -1 to +1, excuse me. So does the derivative exist everywhere between -1 and +1? You can already look right here. I see that sharp corner. Remember that the derivative does not exist at sharp corners, at cusps, at vertical tangents. These are the things we need to look out for. Which means no, it is not differentiable on a to b. So that means that Rolle's theorem does not apply. Rolle's theorem does not apply. We didn't even get to the third condition. If any one of these conditions fail, you can say, no, you know what? Rolle's theorem does not apply. You don't need to do anything beyond that.